in the, okay. And because I don't have a pointer, I need to find that. Go ahead. That's hopeful. Okay, I'm blindly trying to find the bottom because I can't even exit my screen. And there we go. Sorry about that. So yeah, my name is Luis. I'm a lecturer in the Earth Science and Engineering department. I do teach deep learning to master's students, and I work in deep learning methods combined with ultrasound imaging. And today I'm going to talk about something that's inspired by ultrasound medical imaging, but that is completely unrelated, or at least the application of the method is completely unrelated to it. So the title of the talk is Divide, Convolve, and Conquer, and that hopefully will become clear in a few slides. And we're doing data comparison with Wiener filters. And this is a work with the joint effort with the guys in my team. You put the names in here. So I'm going to talk a little bit about the motivation. I mean, I think it's interesting because somehow this method is arise quite serendipitously from us trying to solve a completely different problem, and then we found this solution and we realized it could be applied to other fields and many other settings. And I'll talk a little bit about the Wiener filters themselves. Some of you might be used to using Wiener filters, mostly for data denoising and things like that. That's not how we use them, so it's worth perhaps clarifying that. And then I'll show you a few examples of applications and some results that we've obtained so far. So the idea comes from one of the problems we were trying to solve a while back, maybe a year and a half ago or something. We work with brain imaging. We want to have access to big brain data sets. Most of these data sets are incomplete and they have gaps in them. So basically we wanted to find a solution by which we could take images on the left, which correspond, for example, to a CT scan that has some gaps in it, and reconstruct images that have like fully populated volume pixel values. So how can we do that? So the super simple obvious choice would be to do some sort of bicubic interpolation, which is not very good, as you can see. But then we tried, and we use an autoencoder with an MSC loss standard practice. And then it does work, it does something, but it doesn't really capture the level of resolution that we need in our data. So that was the problem that we're trying to solve. This is not well resolved enough. Well, why do we care about that, right? So my research is based on something called full waveform inversion. And what we do is we take ultrasound data from sensors surrounding a particular target. My current project is focused on brain, for which a solution does not exist. And we hypothesized that we could actually obtain high resolution images of the brain using only ultrasound. And in here you can see more or less the setting, how the helmet would look like, and the 3D reconstruction and the evolution of this reconstruction, right? You can think of it as a recurrent neural network, if you want, where we're updating the weights and biases of the speed of sound of the model, right? So we just go over and over, iterating to refine this model based on the data that we have. So in order to do that, we want to use, this is a very ideal case, obviously, that's an in silico or numerically simulated result. We can't really rely on this kind of optimal conditions when we work with real data. And we're building large data sets of 3D models, volumetric models of brains. But very often these big data sets are incomplete or have the kind of gaps that I showed you a couple of slides before. So this is more or less the rationale. That's where I'm coming from. That's how we came up with this solution of, okay, we need to find a better way to fill these gaps that we can see in here on the left. So the first thing that we questioned ourselves perhaps is, well, what is the problem with the current methods? Why just a simple autoencoder with an MSC loss wouldn't work for us? And it's quite obvious why, I think, because the kind of MSC-based losses, basically, they focus too much on pixel-wise difference, and they don't really care much about what's going on in the rest of the image. So basically, you take a network output that's not trained, it's initialized randomly, sorry, and the first pass, gives you this random noise on the left, and then you subtract it from your target to get some sort of loss, and then you square you take the delta norm if you want, with a couple of terms of the image on the right. But this image on the right, all these laws, all these error concepts is only somewhat applicable at pixel level, right? There's no concept of what's going on in the rest of the image. Nonetheless, when you do this kind of things, the assumption is that you take one image, and once the network is behaving properly, then the difference between what you produce and the target is zero. And that is what you're aiming for. That is your definition of two images being the same. So we started questioning, is that the right thing to do? Can we do it different? So abstractly speaking, at least, in an abstract way, you could think of a very simplified representation of the problem, and in MSE, you basically say that if x minus y is equal to 0, then x is equal to y, right? But you could also think, you can divide one by the other. You can say, well, what happens if x over y is equal to 1? Obviously, then x is also equal to 1. But that's not straightforward in terms of, you don't want to divide two images pixel-wise, right? Dividing images pixel by pixel is not a very good, it doesn't really get you out of the problem that we had before of lacking contextual awareness. So we started thinking, instead of doing this division in the normal domain, we can think of similar operations to multiplications, and these similar operations, if you want, they could be convolutions, right? So what we're doing now is we're thinking, okay, I've got a network, it's not initialized, it's not trained, it's randomly initialized. It produces some output, it looks like random noise on the left. I can calculate, if I know my target, which is this number 3 from MNIST, for example, I can calculate a Wiener filter that when I convolve it with my target, it gives me my output, right? So if I convolve these 3 and this weird red and blue image on the right, the full convolution of these two guys will give me the image on the left. So that's, at least I've got a different way of combining the output of the network on my target. But I also know that if that Wiener filter is to do an identity operation, all the energy, if you want, all the values, all the spread values around the image on the right would be concentrated in the middle. It would be a value of 1, and all the rest would be zeros. So that if I convolve the Wiener filter, the identity Wiener filter, if you will, on the right with the target, what's going to happen is that I'm going to leave the image completely untouched. So this is a different concept to that one, where we say that the difference is equal to 0. That's kind of an identity operation under addition. We could think of it as an identity operation under convolution, and we can try to exploit that. These Wiener filters, as I said, these Wiener filters in here, when the two images are different, they're full of energy all over the place at different lags, as they call, where imagine the lag is like in the middle of the image is 0, 0 for lag values. And they're very trivial to compute, really. It's just an optimization problem. It's a linear program, really, and it has a very straightforward solution, which is highlighted. And apologies again, I don't know where my pointer is, but it's this formula that's got a box around it. It says that my Wiener filter is simply the cross correlation of an image y to the -1. So inverted, this matrix, it's a matrix, I'll get to that in a second, times the cross correlation between this image y and the image x. And the way that we represent images as Toeplitz vectorized matrices, so basically y is taking your 2D image, vectorizing it into a long vector and making a big Toeplitz matrix out of it, is so that we can write convolutions and correlations as matrix vector operations. So basically the first line in here, this problem that we're trying to solve, yb minus x, is exactly the same as y, small y convolved with b minus x. It's just a convenient way to represent it so that we can operate with these elements algebraically. So that's straightforward enough. We can calculate these Wiener filters, and given any two pairs of images, we can find the least squares fit matching filter from one to the other. And here's when perhaps it makes a bit more sense, the title of the talk. We do that for computational efficiency reasons. We do it in the frequency domain. So we convert the images, and then we take the Hadamard products and Hadamard divisions between them, and that's when we divide the two images, and then we do the inverse Fourier transform to get back to our filter in the black domain as we like it, right? In here, there's a couple of terms perhaps worth mentioning. The first two, the numerator of this operation corresponds to the YTX. In the box equation here is the cross correlation between X and Y. And we add some noise, lambda. And then we divide that in a Hadamard sense by the autocorrelation of X. I think now that I think of it, it says Y, Y, and here X, X. It doesn't really matter. You could do it either way. I've got the nomenclature wrong here, but both formulations work, and both formulations are equally sensible to use. And basically, we're deconvolving by the autocorrelation of one of the images. And here, hence the name, we're dividing. This deconvolution is a division. It's kind of the engine under this concept of dividing two things in the frequency domain is kind of deconvolving combinations of them in the space domain or image domain or time domain. So this is what the Wiener filters look like. And now that we have this concept of we have two different samples, I'm talking about images a lot here. They could be time series, they could be audio signals, they could be really anything you like. I mean, we're concerned about images, and that's what we're using. And then we can start trying to use these filters in different ways, right? So the first examples I'm going to show you are from using these Wiener filters as loss functions. And the very first problem, obviously, where we tried it is our problem with brains. So we're trying to solve this problem now. And the first thing that we need to do is we need to find a suitable form of taking a norm of these filters in order to use it as a loss. So the filters have the same dimensions as the samples or comparable dimensions to the samples, and we need to reduce that to a single value that we can use as a measure, right? What we do here is we take the filter, V, and we want all the energy in this filter to collapse exactly at zero lag. How do we want it to collapse? Not arbitrarily, not in any way. What we want to do is we want to collapse this energy, weighting when I say energy in the filter, what I mean is the values at all lags. So the actual magnitudes of the filter, the values of the filter at all possible lags. So the energy distribution that is very spread at the beginning of the untrained network, we want this energy to be focused at zero lag. And then when it's focused at zero lag, we want to say that's what we solved the problem, right? So at the same time, we need to prioritize energy that is at shorter lags. And to do that, we multiply our Wiener filter by a matrix T. This matrix T, again, is a big matrix where the diagonal elements are the vectorized representation of this figure that you can see here. Basically, I think that's a bit more clear if we do it like that. I take my Wiener filter, I subtract a delta because I want the solution to be zero when all the energy is at zero lag. So I subtract the energy exactly at the middle of the thing, and then I multiply that with this penalty term, right? So what I'm doing is I'm penalizing energies that are living not at zero lag. And the expectation and the rationale is that these filters will drive the updates in the network in such a way that the energy of the filter will progressively become a spike at zero lag. So again, this is the formula, T V minus delta, and this is kind of the visual representation. If you want, we might make it easier. I think I forgot the 1/2 in there. It doesn't really matter. So this is one of the formulations. There are other formulations. I'm not probably going to get into that too much. This one seems to work very well for this kind of problems we're solving when we're using Wiener filters as loss functions. We don't quite understand why, to be honest. That's empirically mostly. It's not that there's anything special about the formulation at the top compared to the one at the bottom. They both try to avoid trivial solutions where the filter is zero, and they both try to preserve amplitude in the data. So they try to get Wiener filters that have amplitudes that result in posterior convolutions with kind of natural image space with the right saturation and amplitude. So empirically, we see that the formulation at the top seems best. We don't quite understand why. The formulation at the bottom has been used in other fields, and it seems to work better in these other fields, like in seismic imaging. So the first test that we did is running an imputation problem. We call it in painting in other fields. I think imputation is quite specific, perhaps, to medical imaging, or that's what I heard it the most. And we're going to use a classical U-Net architecture that probably we all know and love to try and improve the results that we've had before using MSE as a loss. I think that's a very standard U-Net. We use a MIG function instead of a Likert ReLU or whatever they use. ReLU is they use in here. I think we use a MIG instead. But other than that, the architecture is relatively simple. So we have a target on the left. That's what we want to get. I zoomed in a little bit just to get a better idea and to be able to assess the results of what we're getting. And these are the three different lines represent three different samples that have gone through the network once it's been trained, right? So the input is masked. That's what we get, and what we want to recover is the target image on the left. So by Cubic interpolation, as you might expect, it's not very good. It's too simplistic. It relies only on the information available on the sample as you use it. The MSE-driven U-Net starts to do something a bit better, perhaps, even though it's not so obvious, but it still lacks a lot in resolution. And when we plug in our Wiener loss, you can see that the resolution has improved quite dramatically. And particularly, I'm driving your attention here to the cerebellum, where there's fine-grained structure that you can start to discern a bit better when you use a Wiener loss. Some patterns as well, perhaps you cannot see them remotely, but there's some checkerboarding patterns in the images on the right with the Wiener loss. Also in the MSE, I think the MSE, the more due to staircasing, due to the pixel nature of the loss. I think in this case, probably there's some frequencies in the Wiener filter that are kind of going a bit wacky, and the lambda value that we use to precondition to pre-whiten and stabilize the division might be acting up. We're still trying to understand lots of things. But the main message is it seems to work very well. It does a much better job than MSE. We haven't modified anything in terms of network. The only thing we've done is change the loss. We've taken out the MSE loss and we've done some loss. Yeah, I've got a bit of a zoom in here, perhaps. It helps to appreciate better the higher quality of the Wiener loss results. Couple of graphs, training and validation for both the Wiener and MSE. Wiener on the left, MSE on the right, 300 epochs. It's interesting, just the loss plots themselves, as always, to be honest, they don't really tell the whole story. And also, the MSE has very good agreement. I don't think we're overfitting or even underfitting much. I mean, there's very good agreement between the training and the validation curves. In the Wiener loss, instead, you start seeing some divergence between the two. We've thought very hard about it. We don't think it's overfitting, really, because the results that we get are pretty stable, and we're not start going too crazy with the test set, or with the validation set. But again, it's a behavior that we've observed in the other case as well, as I'll show you in a second. So if you have any ideas, why would that be? I think they're more than welcome. So another application we've tried using the Wiener filters, to drive the loss. In this case, we use a very simple autoencoder. I think it had 3 encoding and 3 decoding convolutional layers. We use it on CelebA. We resampled CelebA a little bit to 64 images, just for memory reasons and to be able to do more testing. And in this case, we observed something slightly different, perhaps, but we still win on resolution, I think, with respect to MSE. So if you look at the bottom row, these are the results of training, if you put the autoencoder with the Wiener loss. These are test samples. And the resolution of pretty much all faces seems to be better. There's better definition around the eyes, mouth perhaps, and nose. I'm not going to present it today here, but we have, for some reason, the Wiener Loss is very fixated with the eyes. It really likes to make the eyes bright and important and the centerpiece of the whole thing. I don't know if it's because they're in the middle of the figure or why, but it seems to like that. And the MSC is still a bit blurry. I mean, as it would be, right? It's an MSC. It's Gaussian noise if you want at the end of the day. But the saturation that we get in the Wiener Loss is not quite right. I think the coloring is slightly off. It tends to gravitate towards gray or more kind of gray tones in the reconstructed images. But all in all, I think it demonstrates that it is more sensitive to high frequency content in the images, and it's able to better recover those. Again, a bit of a zoom. Again, keep in mind, these are 64 by 64. Really, you can see the pixels in the images already. But if you look at a couple of examples here, the one on the very left, it seems that the resolution is really improved. And a few more, I think, show the same trend. At least you don't have this feeling of blurriness when you look at it. Again, if we look at the curves, MSC seems to have good agreement. The gap between the two is pretty minimal. Whereas we start to have more noticeable divergence in the Wiener Loss. Again, we don't think we're overfitting all too much, and we don't think we're doing anything too strange with it. And the trend is still both, even though it's not very easy to appreciate in here, in the Wiener Loss curves, the trend is still going downwards. We haven't plateaued, and definitely we're not increasing the value. It's still going down. But I don't know, perhaps we need a larger number of epochs for this particular example. And then we'll see a jump in the validation loss evolution. Two metrics, perhaps, to compare these two examples I've shown so far. For the Celavei autoencoder with MSC and with Wiener Loss, I'm showing, forget about the first column, I don't think it's a measure that's very interesting. The second one shows the MSC loss for both methods. The one that says Wiener Loss obviously shows the Wiener Loss for both methods. So we want to know whether they satisfy each other's criteria of similarity to some extent. And I think, they somewhat do. Not very well, but maybe the gap between the Wiener Loss Celavei autoencoder results under an MSC analysis, if you want an MSC, looking at the MSC values, it seems to be a bit better than trying to figure out how good is the Wiener Loss for the Celavei autoencoder with the MSC, and the same with the imputation case. The structural similarity index measure doesn't seem to be all that different between the two losses, and perhaps where we start to see better performance in the Wiener Loss is when we look at the Fresnel inception distance or the learned perceptual image height similarity. These two metrics are, in general, used to assess the quality of generative model produced images. So I don't know, we think it's perhaps a good measure, and it's a good indication that we're not completely on the wrong track. The fact that these two measures are better in the Wiener Loss cases. I'm going to switch gears a bit here. So then we started thinking this concept of data comparison, data similarity can be used in all sorts of other ways. So you don't really need to use it as a loss, right? So we started thinking, well, can we use it as a non-parametric generative modeling? And that's George. I think George is in the call. So if you have any very specific questions about that, he might be able to answer later. He came up with this idea of, why don't we use a Langevin-Markov chain Monte Carlo diffusion process where we build our energy landscape based on Wiener filters, right? So I'm not going to get too much into the details, but that's kind of, if you're familiar with diffusion, you keep sampling, you have a schedule, and what we do is we update our samples by navigating this energy landscape and adding a bit of noise. So I think this ZT element is important. The schedule step size is not, it's a decisive factor. It's how big a step you want to take. Of course, you've got to get the right one. But the important bit here is the noise added. the ZT nodes, which is sample from a random distribution. And the reason for that is that we want to avoid collapsing into a single sample. So you need to have some degree of variability in your generated samples in order to not collapse to one of the samples in your training set. And then what we do is we basically define the energy, this energy that we need to take the gradient of, as a combination of two different terms. So the first one is, it's called the Rayleigh coefficient, but it's basically the same loss that didn't work for the autoencoders. Now it seems to work very well for the diffusion, for the Wiener diffusion. And that, again, controls, it tries to force the energy of the filters towards zero lag. I haven't talked too much about the filters themselves yet. That hopefully will become clear in a second in this case. But it tries to push the energy of the filter towards zero lag. And then the second term, it controls sensitivity to the amplitudes, right? So I think that would be the analog problem of not getting quite the colors right in the autoencoder with CelebA. We need these filters and we need the generated samples to be sensible in terms of amplitude, absolute amplitudes that they have. So by controlling that the spike in your Wiener is 1 and not any other value, that seems to help stabilize it. The difference, though, is that this T, which is similar to the T we used before, this penalty term, which used to be an upside kind of high values at the middle and decaying values as you go to further lags, now has the opposite shape. So if you want to think of it this way, on the image on the left, which is the penalty we use for data compression and imputation, the yellow is high, is 1, and then you decay. It's kind of a very thin, a very narrow Gaussian into D if you want. Whereas for Wiener diffusion, what we need is the opposite. We need the purple values to be 1, and then we need this 1 to decay and create kind of a hole, like a sinkhole in the middle, where the gradients would get higher and higher as we get closer to the solution. And this particular shape of this thing, we believe, controls a lot of the performance of these Wiener filters, of this Wiener diffusion, if you want. And we're still trying to figure out which one is the best. We've tried a few. We know that some of the shapes we've tried work well. The exact parameterization probably can still be improved. So theoretically, though, on paper, both strategies could work equally well. I mean, you're trying to suppress energies that are not at zero lag, and the way the relative weight of the different lags, it theoretically shouldn't affect it, but in practice it does. So empirically, we find that this strategy, this way around, works well for the two different problems we try, if that makes any sense. So a few important aspects to that. In principle, we could use this Wiener diffusion concept. So this energy landscape that we're going to navigate to try and generate new samples, it could be applied directly on image space. But what we found, again, empirically, is that that's quite finicky. And it's much easier to work on latent representations of the images, if you're working with images, I suspect. 1D kind of samples time series on the sets would behave similarly. But what we do is we encode the images into a one-dimensional latent space with an autoencoder. And then what we do is we try to apply this Langevin dynamics onto this latent space. So it's non-parametric. So once the network is trained, the network that takes your image and put in the latent space, you don't need to touch the network. The network is fixed. You could even use a pre-trained network for that. You don't really care too much. What we do is we take all these samples in the latent space, and with only 500 of these samples, that's enough. I mean, probably you've trained the network with many more than that. But once the network is trained, you just need to take 500 training samples, that's images that you know are good, and you want to make something similar to these images, and put them into this latent space representation, and then solve the problem of navigating, of creating new samples according to this derivative of this gradient of energy based on only these 500 samples. And that's quite attractive because in generative modeling, normally most generative models are very greedy in terms of data. And having a generative model that works with only 500 samples, at least for us, seems to be super attractive. The figure on the right shows the evolution of these latent space representations. And they are not filters, these are latent space vectors, basically. Take an image of MNIST or whatever, encode it into a 31 sample representation, 1D vector, and in black you can see the training set, and in red is a few examples of the generated samples that we create using the black lines if you want to drive the whole process. Each one of the red samples obviously are generated independently, and here we're just showing them all together for visualization purposes. But what you see is that the red samples tend to collapse to different modes, to collapse to different shapes that are not any of the individual shapes that already exist in the black, if you know what I mean. They look like what they should look, but they don't collapse into samples of the training set. And I'll demonstrate that in a second, a bit of luck. So the first thing that we do, because we like brains and we work with brains and we want to use all sorts of crazy stuff with big range data sets to enforce priors in our image reconstructions and things like that. We tried, can we use that as a cheap way to generate new brains out of a few samples that we already have? So in here on the left, in this case, we use a latent space size of 51 with a simple autoencoder. I think probably might as well be the same very shallow encoder we use for the Celerbe problem. And in the left, you can see the animation that shows how these samples evolve from not quite random noise. I mean, they already, image kicks off a bit higher up, but you can see how it evolved, right? And on the right, we can see for a bunch of them, you can see what's really happening here. So what we're showing is the top row of every single one of the rows on the right is, or the one with the brains, it shows at every step of every few steps of the generative process, how does the brain start to look like a brain? And on the bottom, what we have is the Wiener filter, not this latent space representation, but the Wiener filters between my randomly sampled latent space vectors. I'm going to take a random sample of this, so something that doesn't look as well structured as the black lines here, if you want something that's completely random. And I'm going to calculate Wiener filters between this random thing and all the black lines that we have in here. And that's going to define my landscape, my energy landscape, and then I'm going to be optimizing the Wiener filter so that it kind of starts to become a spike. And when I'm done with it, the latent space representation that gives me a spiky Wiener filter, I'm going to decode that, and that's going to be my generated model. So again, I don't need to train the model, I just need to play a little bit with the representations in the latent space. So a bit of a zoom, perhaps I don't know if it's very helpful, some of you might not see it very clearly, but you can see how it doesn't really appear, it does deform. For us, it's important, right? I mean, it does start getting a shape, and it conforms to the shape of a brain, of a skull, and it gains the continuity, and at least perceptually, they start to look like samples of a big data set that we can use to impose priors, or as I said, or other types of constraints in our image reconstruction process. Same thing with MNIST. We could do exactly the same. I'm not going to probably waste a lot of time here, but you can generate lots of images with MNIST. The reason why I'm doing this with MNIST is because it's much easier to convince you, at least, after we've convinced ourselves, that we're not collapsing to any of the samples that we already have in the training set. So how do I convince myself to that? So if I have true samples on the top left panel and generated samples on the top right panel, now the bottom left panel shows the distance, the difference really, between the generated sample and the closest sample in the data set. So we can find what's the closest sample in the data set, take the difference, look in red and blue, the values of this difference, and then we're going to do the same thing again between the closest and the second closest. And what we're expecting to see, if we're not collapsing to any particular sample in the training set, is that the two images at the bottom look very similar qualitatively and even quantitatively. It's not, we are kind of saying here that we are as far to the closest sample as the closest sample is to the second closest sample. And the closest sample and the second closest sample, they both in the training set, we haven't touched, we haven't done anything with that. We're just trying to understand if we're collapsing to any particular, I think we're not. So I think think that illustrates it well. Doing that with brains is a bit more tricky because the images are super messy, but with numbers in MNIST, it's quite obvious that this is the case. Again, we can do that with CelebA, and we can generate faces. There's still lots of artifacts. It's not, we didn't put massive effort into it. We just played a little bit to see if that were working here. It seems to be working. I'm sure that with a bit of fine tuning, we could make it work better. And I'm pretty sure that you're already quite fed up to listening to me. So I'm going to give you a final bonus application of this thing, and that's translational invariant metric. And I think that perhaps it's the least explored of the methods we've done, but perhaps it's the one that has more application to scientific problems that several people in here, at least in our department, are trying to work. So we want to use the concept of Wiener filters to build in this case, a classifier. It doesn't have to be that. It's just we're trying to understand if this concept of distance works well. So we have a KNN classifier where we define the distance based on a normalized filter. So V minus mu V over sigma V is just a normalized filter. We take the maximum value of this filter, and for a new sample that we want to classify, we calculate all possible Wiener filters between this sample and my training set, every single sample in my training set. And I'm just looking at all the filters, because the filters are normalized. I just look at the maximum value. What is the filter that has the maximum value? With the expectation and the hypothesis that this maximum value will be in a filter that looks like a spike. But now this spike doesn't have to be at zero lag. It could be anywhere it wants. What we're saying with a spike Wiener filter at zero lag or any other lag is that the shape of the thing that we're trying to classify looks exactly like another one that might be put in a different position. But this is still the same shape. It's a bit of a crude approach, to be honest, but I think it can be refined quite further from this point. But it seems to work quite well, to be honest. To validate that, we've taken MNIST as a training set and AFNIST as a testing set. So we take a sample from the AFNIST, which is the testing set on the right, which is MNIST moved all over the place, and we calculate all these Wiener filters between this sample in the testing set and all the samples in the training set which have not been rotated or moved or translated in any way. And then we try and pick the maximum, the filter with the maximum value. The filter with the maximum value corresponds to a class in the training set, and that's the class that we assign to. It's not perfect, but it goes from 16% accuracy using a Manhattan distance metric to a 61% accuracy with our method. And to the right, you can see the configured matrices for both methods, and the Wiener translational invariant metric seems to perform much better. It seems to be heading into the right direction, at least. It's not nearly as good as you'd like it to be, but it seems that it's got value in terms of being quite robust to translational invariance. There's a whole other question, which is what happens with rotations, where filters are not so well structured, and we're trying to understand that too. And that would make it, I think, a genuinely very powerful tool for any scientific problem where you want to enforce translational and rotational invariance. And I think that's it. So conclusion is not really a conclusion, it's more of a where are we going from here? So we need to polish this a lot. We need to understand how it works mathematically, empirically, and in all sorts of ways. We also expect that there might be many more applications where this concept of comparing data in a different way could be applied. And yeah, if you're interested in testing it in your research, if you think it's something that could be useful, please reach out to me, anyone in my group, and we'll be super happy to collaborate and continue working with developing this new idea. Yeah, I hope you find that interesting. And yeah, I'm more than happy to take questions, and with a bit of luck, we'll have a bit of a discussion around it.
Thank you, Luis. Can you hear me?
Yes, probably I took too long. Apologies for that.
No, it's perfect, like on time. We have enough time for questions as well. So if you have any questions for Luis, just type them in the chat, or you can raise your hand and ask them directly. Maybe I'll start with a question. In terms of what are the scalability issues that you foresee of using like a Wiener loss and maybe like a larger image, or will it make the training a bit slower?
Maybe, not really. I mean, I think the bottleneck really is there's two, I guess, but the main one is the Fourier transforms to calculate the Wiener filter. Nowadays, these things are super optimized. The problems that we're having when we're trying to scale this problem to larger images and things like that is much more, it's less computational bottlenecks and much more conceptual bottlenecks. We don't understand why it behaves the way it behaves. For example, when we go to Celebi with larger images, we start getting super creepy faces with saturated eyes and nose and very sharp resolution, but completely the wrong colors in the image. And we're still trying to understand why, to be honest.
Okay. Yeah. And in terms of like, sorry if you mentioned this, but is it just, can you use in something else that's not images? For example, like audio, can you transform the Wiener loss into something?
I'm sure not only you can, I think it'd be even better. I mean, we had a problem with images and had to deal with them. The original idea of using these Wiener filters comes from a different optimization problem in geophysics, which is similar to what I thought with brains. People use the same method, or actually I use the same method to image the subsurface of the Earth. And in this case, the data is one dimensional. It's seismograms, right? So it's like an audio trace. And because it's an audio and it's got a zero and it oscillates, it's got a very well-defined frequency spectrum that you can control and understand. So it's much more intuitive, and it would be much more intuitive to use it in a 1D setting where you have some sort of audio signals and things like that.
Okay, so you kind of like you move it to like 2D to.
Yes, to be able to tackle this problem, but we've came up with the idea to do it in seismic imaging first. And after many years, and this is working, and it's been out in the wild for a while, and we thought it was a good idea to try it here.
Yep. And in terms, if you go back to the Celeb A data set, you said that, for example, the tones, maybe struggling with the tones is a bit lighter. Is that something that just happens with RGB images, or like what will happen?
Not really, no. I mean, we thought it was a problem with having 3-channel data. Mm-hmm. We've tackled the problem in different ways because 3-channel data has 3 channels. And we could do independent Wiener filters to each channel, or we could do like a combined Wiener filter in kind of 3D. And we even tried to collapse the 3 and just work with black and white images or grayscale images in this. And we observed similar behavior. So I don't think it's a problem with the color as RGB color. It's much more of a problem, I think, of some frequencies, very low frequencies perhaps in the data don't seem to be recovered as we expect. But we don't always see that. Sometimes we don't see it at all and it behaves like a chart. It could be a hyperparameter tuning exercise of finding the optimal parameters, to be honest.
Okay, yeah. But so you see this consistently happening? Like
we see it in Celebi. We don't really see it much with brains. We don't really see, well, in Emlist, you're not going to see it anyway. But it's in Celebi particularly. I suspect there's something to do with the faces themselves. The distribution of the faces is very particular, right? And you've got a high frequency content in the eyes and it's very distinct. I don't know if that has anything to do.
Okay, yeah. Cool. Any other questions for Luis?
Hi, yep. Luis, can you hear me?
Hi, Melissa, I can hear you perfectly well, yes. How are you doing?
All right. A sort of non-scientific question along the lines that Cesar just asked is, in one of the first pictures of the faces that you've shown, since I looked very carefully, just to show you that I followed your talk very carefully, two of the women in the original photos had jewelry, and that jewelry seems to have disappeared after you applied your filter. So is that something to do with the gold color and silver color that you can't replicate, or?
Not really. It's I think it's to do with the fact that the network has kind of smoothed it out. It disappears both with MSE and Wiener losses. So this kind of networks, they try to abstract filters and then work on a particular tightening up a distribution of these low latent space representations. And I think if everybody were wearing jewelry, perhaps they would show up again. But I think they're a bit of an outlier, maybe. But yeah, and I don't think Wiener performs any better or any worse than MSE in that sense.
But isn't that a possibility of a future problem? Because if you have a detail which is unusual, you won't necessarily pick it up, because if I understood what you were saying, we won't focus on that.
It won't focus on that. It will deem it not important because it's not present enough in the data. When you compress it into I think having a more expressive network definitely would not have that. I mean, this is super small toy example networks. If we had like a proper network, it would definitely capture it, but it would need more. Yeah.
Okay, thanks.
No worries.
Thank you. Any other questions for Luis? I can ask another question.
Sure.
For my particular research, usually I work with 3D models, mainly unstructured meshes. So maybe a CNN is not the most appropriate way to tackle it. Maybe like a graph network. We tried with CNNs at some point, but you have to modify the CNN in a way that end up being better to use like graph networks or other approaches to handle it. In the way that you move it from like 1D to 2D, have you tried anything with like GNNs?
Not really. I mean, I think so. 1D to 2D to 3D, our main concern so far has been compute power, really, because in 3D, it's a bit heavy. Graph networks, I haven't thought about. Well, I have thought about it, but I don't really have a very well-formed opinion about them, because somewhat the filters do assume a regular sampling. It doesn't need to be. You could find filters that do something else, but I don't think we have a good answer for what is the analog of a binary filter in graph networks, right? Where you're basically promoting the connections between samples. I think there is one somewhere, but I haven't found it.
All right, yeah. But you see that this potentially could be used, maybe.
Yeah, I don't see why not. It might not be the particular formulation of the binary filter. I think what's important that most people, at least in computer vision, ignore is the fact that throwing more complexity into the network is all well and good, but having a loss that's not complex enough, it's really shooting yourself in the foot. So the images have a lot of contextual information. The audio signals have a lot of contextual information. Text does. As you can see if you use any transformers, right? I mean, there is contextual information to be exploited, and I think I don't know what to do with the graph networks, to be honest. But yeah, it'd be cool if you figure it out. Let us know, and happy to work together on that.
And in terms of like, I think. Sorry, let me check. Any other questions? Otherwise, maybe I can move with like the last question, if that's okay.
Sure thing.
Yep. How will this handle like sparse data? Let's say I'm also working with like a rainfall data set where not necessarily have data in every single part of the domain, and it's quite sparse and it's not always on the same place. Will that...
Do you want to populate the gaps that you have in your data, or do you want to use the sparse data as is to make other kinds of predictions?
Just for example, if like I would like to generate like new rainfall patches everywhere, like that doesn't necessarily mean like those rainfall patches will appear in the training data, or maybe sometimes they are, but not all the time. So it's kind of also related to remote sensing. Sometimes with satellites, we have data in certain patches, but not everywhere, and not all throughout the whole data set, not always at the same place. So in that kind of variability or like a sparse data, how do you think like the winner loss?
So we're working quite actively on that right now. I think if I understand your question right, you're asking me about unsupervised learning, right? I mean, what happens when? We are trying to figure out a way to mask the information in the data, but unmask it's not a mask directly in the filters, but only generate filters that are aware of the partial information in the data, which is different to the imputation problem I showed, where eventually you do have access to the full coverage of information. What happens if you never have that, and how do you get away with having gaps in the ground truth data? We're thinking about it. Let me say that. We've got a couple of ideas, but we haven't tested them yet, and they might be completely useless. So.
No, it seems very interesting. It's always like good to know like different kind of losses, and like it's not always just like an MSC and that's the solution to everything. And
Yeah, I mean, I haven't shown everything here, but we've also compared to focal losses, which you might think they are kind of somewhat related, but I don't think they are. I think focal losses are MSE losses in these guys, if you ask me. But I mean, people have published it and they looked at it, so we've compared it with that, and we see. Yeah, we still see an improvement compared to these in some cases.
Yeah, super interesting.
Cool.
I think we can leave the talk up to here, if that's okay, Luis.
Excellent. Thanks for having me this time. Thanks everybody for attending.
Thank you so much for sharing your time with us and for everyone to attending the seminar. So,
will you send me the recording when it's ready? Or will you let me know what it is?
Yeah, we'll process it and then I'll send you the link when it's available.
Excellent. Thank you very much. All right.
Thank you very much. Bye, everyone.
Cheers. Bye now.